Hi, this is Dr. Anna, your physical geology professor, and our topic today is the running water. So, probably you all figured this out by now that running water is probably one of the most important topics we're going to cover because it's a very important geologic agent. It erodes and transports material, it deposits sediment, and basically every earthscape or landscape on Earth is related to the running water activity. Of course, the groundwater is going to be important also. That's the next chapter. So we'll talk a lot about that too. This slide actually shows the distribution of the water on Earth. And you can see that most of the water is in the ocean, 97.2%. So basically 2.8% is in everything else. And you can see that if you think of that 2.8% right here, most of that is still in the glacier. Like Antarctica has huge glaciers. The higher mountains have Greenland, Iceland have major glaciers. So only 0.6% is in the ground, and then even less is what is in the water cycle. That's what the rivers, the lakes, all those kind of water. So you have to kind of think it differently because you can see how little amount of water which is in the water cycle which you can handle. That's what we need. We need to drink it, because how long can a human go without drinking? You're right, if you said 2-3 days, that's the maximum amount you can go without drinking. So the running water is extremely important. Next thing we'll have to talk about is the hydrologic cycle. And these are the words you kind of have to know on the hydrologic cycle. I know you learned it in elementary school, but the one you got to know now is a bit more detailed. These are the words which have to be there. The evaporation, the water evaporating from the ocean. The precipitation, when the clouds go over the land and it rains, that's the precipitation. Then you get the transpiration. The plants are using water, so they are taking a lot of water and then they will release some of it, and that is what we call transpiration. So that's the precipitation, evaporation, and then the runoff is the water which runs off after rain on top of the land. So the runoff is right here. And then the infiltration is as the water actually goes underground to make the groundwater. That's the infiltration. So these are the words which if you draw the water cycle has to be on it. So you can just draw a very simple diagram here like that. Right here, and this is like not very good condition, but here we have the trees. So the transpiration goes there, then you got the ocean here. And that's where you got the evaporation, the clouds move over with precipitation, you got the runoff, and then the infiltration, which makes the groundwater. So this is how you can draw it. Now, the evaporation and the transpiration together is called evapotranspiration. I might ask that word, so you should know it. Evapotranspiration. And here is the close-up of the drawing. So make sure that you have the runoff, infiltration, the evaporation, precipitation, and transpiration from the plants. That's basically pretty easy, and it's easy to draw. Okay, so let's jump. When we're talking about rivers and river activities, the scientific name for it is fluvial system. Basically, it's the running water, which means anything which relates to rivers. And the running water basically have probably the largest influence on us throughout the Earth history. because it's important for us for drinking water. It gives us energy, it lets us travel, and it helps us with irrigation. So there is a whole lot of purposes of water, and without it, as you know, we could not be here. We have two kinds of big group in terms of running water. One is the unconfined flow, and the other one is the confined flow. The confined flow, basically, scientific name for it is stream. So unconfined flow is when basically the runoff, when the water is flowing on the surface and it's unconfined, which means it doesn't have channels. If the slope is low, if the slope is slow, the ground is just doing sheet flow, it's just flowing on the ground. But when the slope is greater, it will make this slow scours or rills. So that's important to know. So this picture is a typical sheet flow. You can see how the sheet of water is flowing on the surface. This is typical runoff, where it's very gentle slope, so the water just runs off as a sheet, and we call it sheet flow. And then when the slope gets a bit steeper, then you will see these small channels which are eroded by the moving water, and we call them rills. And if you think of it, the rills are actually moving up as more and more water comes down. These rills are creeping upward. On the other hand, when the flow is confined, we call it stream, confined flow. The confined flow is confined into the channel, which is actually made by the stream, and it happens by the erosion of the stream into the underlying rocks. This is talking about the important parts of the running water. Basically the stream, actually the confined flow. Usually the stream starts up in the mountain, and these are important parts, like the headwater parts, which is where the stream starts. Then you got the mouth part, when the stream enters into the ocean, and then you have the banks, the stream banks on the side of the stream, and the floodplains which are surrounding the stream. So these are the important parts of the stream flow. And this is the so-called longitudinal profile of the stream, which actually goes all the way from the headwater, which is the beginning of the stream, to the mouth part of the stream. And if you look at it on the side, you know, you see a very, very nice concave up curve, and that is the longitudinal profile of the stream. And we'll talk about it later. When it's really nice concave up curve, we call it graded stream, and as I said, we're going to talk more about that. So the longitudinal profile takes us to talk about different parts of the stream a little bit more. If you think of the headwater part, what is characteristic of the streams at the headwater part is that the streams are making typical V shape, and on the test I will ask you to draw it and label it. So putting the V shape is important for the headwater part, and actually the stream itself occupies the bottom of this V. There are no floodplains usually in the mountains, but when you're close to the mouth, usually the stream is really wide, and the channel is wide and shallow, and surrounded by well-developed floodplains. So this is very characteristic of the mouth part of the river. So if I ask you to please draw and label the longitudinal profile, this is what you have to kind of sketch. Just exactly the same figure, with the two places, the headwater part with the V-shaped valley, and the mouth part with the very wide channel and the big floodplains around it. So what does this slide show? This is showing, I hope that's what you said, a very typical V-shaped valley. Look, this is the V shape, and the channel occupies the bottom of the V, just like here, V shape. Water is in the bottom of the V shape. So these are typical headwater part of a stream, and this here is the typical mouth part of the stream. As you can see, it's really wide, and actually it's surrounded even wider floodplains. So the mouth part of the stream is very wide, shallow channel, with big time floodplains around it. The flow in the channel can be two kinds, the laminar or turbulent. And I have a really good drawing here. We don't really have to talk about it much. When the water is laminar, the flow is laminar, the particles are flowing parallel with the stream banks. When it's turbulent, on the other hand, the water flows in erratic fashion, so it's not parallel with the banks. It makes swirling and whirlpool-like eddies. Those are the ones you have to be careful because they can pull you down. So when you swim, you have to be careful with turbulent water. Next thing is the factors which are affecting stream erosion and deposition. One is the velocity and the other one of the discharge. So we have to talk about those guys now. Starting with the velocity. Normally when the stream is straight and the channel is symmetrical, then the fastest moving part is usually right in the middle here. Not on exactly the top because the air resistance, not in the bottom because of the roughness of the rocks on the bottom, but it's about right there. Now, when the river moving relatively fast, it's about 50 miles an hour. When it moves slow, it's about 3 miles per hour. When the velocity is really high, the stream will erode and transport sediment. When the velocity is low, then the river will deposit sediments. The velocity of the stream is controlled by two very important factors. One is the gradient, and the other one is the channel shape and roughness. So let's start with the gradient. When we're talking about gradient, we're talking about a slope, a natural slope, and we want to calculate how fast the water moves on it. To know that, you have to calculate the gradient of the stream between A and B. Here, A, B. And the way you calculate it is that you get the elevation difference, which is H. This is an H. And divide it by the length between A and B. So that's L. So the gradient is going to be equal H over L. Usually the elevation difference is going to be measured in feet, and the distance will be measured in mile. So it's going to be in feet per mile. But if somebody asks you to calculate the percentage, then the most important thing is that one of the unit has to be turned into other. So when you want G percentage, then it has to be H over L. Both unit has to be the same. Then you can multiply it by 100. And then that's going to give you the percentage. So depending on how somebody asks you, this is the way you have to calculate it. Now the elevation difference can be, you can get the elevation difference if you use a topographic map. You can get the elevation difference using the contour lines. The contour lines are giving you the elevation at a certain point. So you can calculate the elevation difference with the contour lines, and then the distance you can calculate using the scale. If it gets there, I will show you this in the lab, but it might not get there. But it's easy to actually get it. Now, if you look at the longitudinal profile of the stream, you see this is from the headwater all the way to the mouth part. Then easy to see that in the headwater part, the gradient is going to be steep. Usually when we say 15%, that's a pretty steep gradient. 15% is steep gradient. When it's very, very gentle gradient, usually it's 1 to 2 degrees. 1 to 2%, sorry. So the channel shape and the roughness influences the speed of the water because there is a friction. And of course, the larger the channel, the larger the bank, the larger the friction. So the smaller the stream, the smaller the friction. So therefore the water can flow faster. The next one is the stream discharge. And when you're thinking of the discharge of the stream, you have to think that we always have to calculate the volume of the water in the stream channel. So if that's the full channel, then how do you calculate the volume? Basically, you multiply the width of the stream with the depth of the stream and the speed of the water in it. So to measure the width, that's a problem because you understand anywhere you measure it's a different width. And the same with the depth. Anywhere you measure it's a bit different. So therefore it's a higher level calculation really. You have to use differentiation, integration to calculate the stream discharge accurately. But this here is the way you calculate. Discharge is D, and that's equal with the width, which is going to be a meter, the depth, which is also a meter, times the velocity, which is given in meter per sec. So the discharge will be meter times meter times meter per sec. So it's meter cube over second. But how do we get over this problem that everywhere you measure the width, it's different, is that you have these so-called gauging stations. So people can measure at every water level, they can measure actually the width of the stream, so they can get a much better value for the discharge of the stream. Okay, the next thing we have to talk about is the stream erosion. The stream erosion, usually the streams usually cut their own valley, own channel by so the streams can actually cut their own valley by deepening and widening for a long time. The stream erosion can happen in three waves. The hydraulic action, which is the ability of the flowing water to pick up and carry rocks. Then you have the second one is the solution. The solution is when the chemicals dissolve from the rocks underneath. And the third one is the abrasion. The abrasion is basically the grading, carving of the river bed rocks. You have to imagine that the water picks up low rocks and starts actually making swirling, and it drills into the rock and makes these really typical potholes. So this is another thing you can take pictures of, so just do it. I hope you're going to have really great picture projects. You have so many pictures you can take that it's unbelievable. So I hope you will do a good job on that. Now the sediment in the river can be carried three ways. One is the bed load. Those are the large sediment particles which usually sit in the bottom of the water, and very rarely you see it moving. Most of the time you don't, because when they move you're not there, because that means the river is flooding. So this largest grain size can be moved two ways. One is the saltation. Saltation is when the stream picks up the rock and puts it down. The other way is when it drags it. So it's just dragging it on the bottom, dragging. So this is the saltation, and this is the traction. The traction is when it's just dragging it. So the saltation is when it's picking it up, putting it down, and the dragging is what we call traction. So just remember that. The bed load can be moved by saltation, or dragging means traction. Then you got the suspended load. The suspended load is the sediment which actually can carry it in the flowing water. That's what makes water dirty water. You know, when the water is muddy, that means that it's flooding. That means that it's all the silt-sized sediments are in the water all the time. When actually it's not flooding, it's slow. Usually this sediment settles, and then the water crystal clear, you can see through. So the suspended load. And the third one is the dissolved load. And the dissolved load is invisible. We are talking about the chemicals which are dissolved in the stream water. Okay, so here is a couple of pictures. These are about the bed load, and this is like, this area rather is the suspended load. Those are the silt-sized sediment. The two more words that you got to know, one is the competence, which is the maximum size sediment which can be moved, and the capacity is the total load of the stream. I will ask true false questions about it. It's kind of important to know. And I guess I'm gonna finish this segment right here because we are at 20 minutes. I hope it's still gonna take it. So I'll see you in the next segment.